Hello students, welcome to lecture 13 MVUE through Sufficient Statistic 2. Recall that a statistic Tx, that is a function of x1, x2 up to xn, is called sufficient if the conditional PDF or conditional PMF does not involve theta. That is the definition of sufficient statistic. And we discussed also factorization theorem. Tx is sufficient if and only if the joint PDF as a function of theta can be factorized into two factors. One factor g is a function of theta and Tx, and other factor hx, that is a non-zero function of x1, x2 up to xn only. So, the same can be written in the case of discrete case also. In that case, probability mass function as a function of theta is product of these two factors. Rao-Blackwell theorem: given an unbiased estimator theta dash hat and a sufficient statistic Tx, we can get an unbiased estimator theta dash, that is given by E of theta dash hat given Tx, which is also unbiased and which has variance less than the variance of theta dash hat. So, that way we can get a better estimator using the Rao-Blackwell theorem. We also discussed complete statistic. Suppose Tx is a statistic such that E of g Tx is equal to 0 for all theta and for any bounded function g Tx. Then Tx is complete if and only if g Tx is equal to 0 with probability 1. That means, if this is equal to 0, expectation is equal to 0, then g Tx must be equal to 0 with probability 1. So, that way we define complete statistic. In this lecture, we will look into some more properties of completeness and see how a complete sufficient statistic can be used to find the MVUE, minimum variance unbiased estimator. We will start with a theorem. If Tx is a complete sufficient statistic, then there is only one function gTx which is unbiased. So, given Tx, there is only one function gTx which is unbiased. So, that is important. Now, if Tx is complete and unbiased, then we can find only one function gTx which is unbiased. We will prove this theorem. Suppose there is another function g1 Tx which is unbiased. So, already gTx is unbiased. Suppose there is another function g1 Tx which is unbiased. Then E of gTx must be equal to E of g1 Tx. Therefore, if I take the E of g1 Tx to the left hand side, I will get E of gTx minus E of g1 Tx, that must be equal to 0. And we can take E outside, E of gTx minus g1 Tx must be equal to 0. Now, Tx is a complete statistic. Therefore, if E of g of Tx minus g1 Tx is equal to 0, then this argument must be equal to 0 with probability 1. So, this will imply that gTx is equal to g1 Tx with probability 1. Therefore, what we conclude that gTx is a unique unbiased estimator. If Tx is a complete sufficient statistic, there exists only one unbiased estimator, that is gTx. Now, we will prove one classical theorem which will help us to find out the MVUE. Suppose Tx is complete and sufficient statistic for theta, and gTx is unbiased estimator based on Tx. So, we have an unbiased estimator based on Tx. Then GTX is the MVUE. We will prove this. Suppose theta dash hat x is any unbiased estimator of theta. Then G of Tx, E of theta dash hat x given Tx is another estimator. Now using Rao-Blackwell theorem, this estimator is unbiased and variance of GTX is less than equal to variance of theta dash hat x. But we know that Tx is a complete statistics, therefore, there is only one function GTX which is unbiased. Therefore, GTX is unique and its variance is less than the variance of any other estimator theta dash hat x. So, therefore, GTX equal to E of theta hat dash x given Tx is an MVUE, because it is unbiased and it is unique and its variance is less than equal to any other unbiased estimator. Therefore, this will be the MVUE. So, we saw that using the Lehman-Cephet theorem, we can find out an unbiased estimator which has the minimum variance. We shall consider one example. Suppose x1, x2 up to xn are IID independent and identically distributed Bernoulli 1 theta random variables. This symbol represents the Bernoulli distribution with parameter theta. Theta is the probability of success. So, Tx summation xi I going from 1 to n, this is the statistic we are considering. We have already proved that this statistic is sufficient and it is complete also. So, there is only one function of Tx which is unbiased, that is according to Lehman-Cephet theorem. Now, by inspection we get that if we divide this sum by n, that is 1 by n summation xi I going to n, this will be unbiased, because you can take the expectation here and there will be n times expectation and n will get cancelled. Therefore, this is unbiased, and I know that according to Lehman-Cephet theorem there is only one unbiased estimator which is a function of the complete statistic. Therefore, this estimator must be an MVUE. So, that way we see how the completeness has helped us to find out the MVUE. Note that in this case we found the MVUE by inspection without explicitly determining GTX. So, this is the formulation, but without this formulation we could find out this quantity. But in all situations it may not be possible to find a complete sufficient statistic which is unbiased by inspection. So, we have to compute this statistic or this MVUE through this operation E of theta hat dash given Tx. So, we have to perform this operation to find out the Tx. We will discuss one important family of distribution for which finding out a complete sufficient statistic is easier. Such a family is the exponential family of distribution. A family of distribution with the probability density function of the form f x theta, that is a function of theta, and it can be written as a theta. One term is a theta, another term is bx, and third term is exponential of c theta into tx. So, if we can write in this form with a theta greater than 0, because it is a probability, this quantity must be greater than 0, and c theta is a real function of theta and bx greater than 0, then this family will be called the exponential family of distribution with one parameter. And now, we can have a multi-parameter exponential family of distribution. Suppose f of x theta is equal to a theta into bx into exponential of summation ci theta into tix I going from 1 to k. Suppose in this form where as in here a theta is greater than 0, bx is also greater than 0, non-negative function, and ci theta is also a real function like this. And then this family is known as the k parameter exponential family of distribution. We can find out an exponential family of discrete random variables also in the similar manner. If the probability mass function can be written in this form, then that family will be called the exponential family of distribution. We will see one example. Suppose x is a normal distribution with mean mu and variance sigma square, and mu and sigma square are unknown. Then the PDF we can write like this: f of x mu sigma square, it is a function of mu and sigma square, that is equal to 1 by root over 2 pi sigma into exponential minus 1 by 2 sigma square into x minus mu whole square. So, this we can write like that is 1 by root over 2 pi sigma into exponential minus 1 by 2 sigma square into x square plus mu square minus 2 mu x. Now, this mu square term we can take outside. So, that way it will be 1 by root over 2 pi sigma into exponential minus mu square by 2 sigma square into exponential mu by sigma square x, this part, minus, because of this minus sign, 1 by 2 sigma square into x square. So, now we can compare this expression with this distribution, and that is there should be a theta term, bx term, and then exponential term in the summation form. So, there we see that there are sum of two quantities here, and this is the a theta term, that is it is a function of mu and sigma square, and bx will be equal to 1, and then exponential terms is the summation of these two quantities. So, therefore, f x mu sigma square belongs to a two parameter exponential family with theta, that is parameter vector, is equal to mu sigma square. It comprises of mu and sigma square. A theta will be equal to 1 by root over 2 pi sigma into exponential minus mu square by 2 sigma square. So, it is a function of mu and sigma square, and bx is equal to 1. C1 theta will be equal to this is mu by sigma square. C2 theta will be minus 1 by 2 sigma square. T1x is equal to x and T2x is equal to x square. So, that way normal distribution is a member of the exponential family of distribution. Now, we will see that complete sufficient statistics for exponential family of distribution can be found from the expression for the joint PDF itself. Suppose if x1, x2 up to xn are IIT random variables of the exponential family, then we can write f x1, x2 up to xn as a function of theta. That will be, because there are n terms now, this term will be a to the power n theta into product b of xj, j going from 1 to n, into exponential I going from 1 to k ci theta into summation j going from 1 to n ti xj. So, this way this is a function of xj we are considering, because there are n terms, we will get an expression like this. Now, this we can write as a to the power n theta into b of x factor, because there is a product of xj terms. So, that we can write as b of x factor. Similarly, here also this summation also we can write as a statistic Tix. Now, my complete statistic will be Tx, that is equal to T1x, T2x up to Tkx, where T1x will be the first summation. Suppose j is equal to 1 to n T1xj, and similarly T2x will be summation T2xj, j going from 1 to n. So, in that way we can find out n statistic from this, and they can be written in a vector form T of x vector. Now, we observed that this joint PDF can be written like this: a to the power n theta into exponential summation ci theta ti x I going from 1 to k. This is one factor which is a function of ti's, that is sufficient statistic, and theta, and into bx there is another term bx which is simply a function of x. So, we can express joint PDF as a product of two factors. One factor is independent of any parameters, it is simply a function of x, and other factor is a function of the parameter and the estimator. So, therefore, by factorization theorem Tx is a sufficient statistic. We have to prove that it is a complete statistic. Next, consider any bounded function of the form gtx. Then we have to find out expected value of gtx to find out the completeness. Therefore, E of gtx, that is integration from minus infinity to infinity of gtx, that is the function, into PDF. Now, PDF is bx into a to the power n theta into exponential summation ci theta tx into dx. So, this integration is the expected value of gtx. Now, this right hand side, because it is an exponential of multiple terms, so this can be interpreted as multivariate Laplace transform, and which will be 0 only when gtx is equal to 0. If this function is 0, only then this multivariate Laplace transform can be equal to 0. Therefore, gtx must be 0 with probability 1, therefore, Tx is a complete statistic. So, we saw that Tx is not only sufficient, but it is also a complete statistic. Now, given the complete sufficient statistics for exponential family of distribution, we can find out the sufficient statistics in this term itself. We can express the likelihood function of IID random variables of the exponential family of distribution like this: f of x theta is equal to a to the power n theta into bx into exponential summation ci theta tix I going from 1 to k. From this representation, we can find out the complete sufficient statistic tix for I is equal to 1 to k. Hence, we can find the MVUE as a function of this Tix, which is unbiased, and we know that only one unbiased estimator exists and which has variance less than or equal to variance of any other unbiased estimator. Therefore, that estimator will be the MVUE. So, we will go back to example again. Let x1, x2 up to xn be IID with all xi's are distributed as normal distribution with mean mu and variance sigma square. Therefore, if I consider only one element, that is x1 only, then its PDF is given by this 1 by root over 2 pi sigma into exponential minus half of 2 sigma square into x1 minus mu whole square. So, this we can express in the exponential family of distribution like this: 1 by root over 2 pi sigma into exponential of minus mu square by 2 sigma square into exponential of minus 1 by 2 sigma square x1 square plus mu by sigma square into x1. Now, for n random variables, the joint PDF as a function of mu sigma square, which is the likelihood function, we can write it as this factor to the power n, and then exponential, because of the product now all summation will come, exponential mu by sigma square into summation xi I going from 1 to n minus 1 by 2 sigma square into summation xi square I going from 1 to n. So, according to our earlier result that this is an exponential family of distribution, and here these are the statistics, these are the complete sufficient statistics. Thus, f of x mu sigma square as a function of mu sigma square belongs to a 2 parameter exponential family with parameter vector is mu by sigma square, and Tx is given by first component is summation xi I going from 1 to n, second component is summation xi square I going from 1 to n, and these two statistics are complete and sufficient. So, therefore, we can find out MVUE using this complete sufficient statistics. So, MVUE will be given by MVUE will be given by first is we have to find out the MVUE for mu hat. This is simple, we have just divided by n. So, that will be 1 by n into summation xi I going from 1 to n. And the other one for this we can show that this function will be given by sigma hat square estimate, that will be equal to 1 by n into summation xi minus mu hat whole square I going from 1 to n. This is not n, this is n minus 1. Then this estimator will be unbiased, and this is the MVUE for sigma hat square. So, that way we see that for exponential family of distribution we can find out the MVUE from the expression for the joint PDF itself. Let us summarize. First point, we note that if Tx is a complete statistic, then there is only one function g Tx which is unbiased, that we have established. Then Lehman-Scheffé theorem, suppose Tx is a complete sufficient statistic for theta and g Tx is unbiased, then g Tx must be an MVUE. So, if we have a function of complete sufficient statistic which is unbiased, then that must be an MVUE. Then we discussed about the family of distribution which is known as the exponential family of distribution. So, it is given by f of x theta is equal to a theta into bx into exponential of k sums, that is I going from 1 to k of ci theta into ti x. So, this is the exponential family of distribution with a theta greater than 0, ci theta as a real function, and bx is also greater than 0 because this is a probability, therefore, this must be greater than 0, and this is the exponential family of distribution. We can express the likelihood function of the IID random variables of the exponential family of distribution in this form, that is the f of x factor theta as a function of theta. This is the likelihood function or joint PDF. This can be written as a to the power n theta into b of x factor exponential summation ci theta ti x I going from 1 to k. We can write in this form, and from this representation we can find out the complete sufficient statistics as Tix I going from 1 to k. We have found out a complete sufficient statistic from the exponential family of distribution, and from that complete sufficient statistic we can find out the MVUE, because we have to find out a function of Tix which are unbiased, that will give you the MVUE. So, that way we saw that we can find out the MVUE by employing two approaches. First one is if we can find out the expression for Cramer-Rao lower bound, then that will give us the MVUE. Next we saw that MVUE can be found out through complete sufficient statistic. But both these approaches involve complicated analysis. We have to apply some simpler techniques to find out a good estimator for parameters. That we will be discussing in the next lecture. Thank you.